We're continuing our discussion about linked lists, and the greatest tool you have in your tool belt when dealing with linked list problems are drawing pictures and adapting your model of how you're going to wire this linked list together as you write the code. So we have two cases here, and whenever you're dealing with linked list rewirings or questions that ask for a special assortment of the nodes, you're going to often have to deal with small edge cases that happen with even or odd size lists. These are things to take into account as you're drawing your cases. You also could draw a single item list, and there's many cases you can test. It's all about edge cases. So we need to swap nodes pairwise. What does pairwise mean? It means for every pairs of nodes going like AB is a pair, CD is a pair, EF is a pair, we need to swap them. So the list becomes BA, it becomes DC, it becomes FE, and then in the odd case, we get BA, we get DC, and then the E gets left alone. The E does not have a pair to match up with. How are we going to approach this problem, and what are our first steps? Our first steps are going to be to enumerate the cases. We've done that to an extent. We haven't gotten the empty case of a null list or a single item list, but we've enumerated an even and an odd case, and we know generally what our inputs will look like. Now there's another thing to ask your interviewer about. You ask them, do I want to move the pointers or do I just move the values? It's often easier just to move the values because when we need to move pointers, it gets into caching. We need to cache memory addresses so we don't lose them when we rewire things. First, we're going to look at just moving the values, swapping pairwise with values. And then we're going to go into swapping the actual memory addresses, swapping pointers to nodes that are next. We're going to look at both. We're going to look at the approach, the intuitions, and the code for both of those. So let's start off by looking at just changing the value. And let's just look at the even case, just so we can get a feel for what this problem is asking of us. If we wanted to make the original list into this list by just swapping the values, it can be as simple as just pointing a pointer at the top of this list, and that pointer right there gives us access to this node. And then we can think about what swap needs to happen. Well, we're going to swap A and B. If we're just swapping the values, we can put a temp variable to cache A's value. So we moved cur's value, which is where our pointer is. So far, we only need a single pointer. Maybe we might need another pointer, but cur.val, we cache the A. And then we can overwrite this A now. We save the value with the next node. And then we can say cur.val equals cur.next.val. Okay, this makes sense. So cur.val equals cur.next.value. The B becomes the A. And then we can say cur.next.val equals this temp. And that means we're going to make that next value what we held, which is A. And then we can make cur.next.next. Where will that move the pointer? To the C. Well, I want to point out something that might be an issue here. So going back to the beginning, remember when we were pointing on the A? What if this was a single item list? We would be able to cache the current value, but if we say cur.next.val, what if that's an empty list? Here's the tiny case I'm talking about. And again, all of this drafting you're doing, if you're in a whiteboarding interview, if you're in a coder pad, this is something you would talk about. These are all the things that would lead you to the ultimate solution. You're slowly crafting how this list will rewire itself as you iterate. Now, this is going to be a problem because we can't say cur.next and then access a value when this is a null reference. We can't access a null reference. So that means that we need to do a check of sorts. Well, we can actually enforce that in our iteration guard. We can say while cur is not null and the next is not null. This is something you can play with in linked list problems. This is a really important pattern I want you to notice. This while guard gives us guarantees. It gives us guarantees as to what cur can be. We know cur will resolve because it can't be null. We know cur.next will resolve because cur.next cannot be null. But the issue is, the more stringent we become with this while loop guard, it might cut off our iteration early. So if we think about the odd case, this might actually hurt us. Or will it? Will it hurt us? So let's think about this. If I have a single item A, will this while loop even enter? It won't, because cur.next is null. If I have a 3-item list, we saw that that worked for the even case, but if I have a 3-item list, what's going to happen? One iteration, it's going to allow us to swap these items, then we go to C. And now what happens? Cur is not null, but cur.next is null. Is this the final list that we wanted? It actually is. That's exactly what we wanted. So we see that this code works on an even list and on an odd list. And since there's only 2 cases for a list, then this is one of the solutions. This is a solution. Well, I don't know if there's any other way you could do this unless you just made it recursive or something, but this is the solution, just swapping the values. As long as cur is not null and the next of cur is not null, just perform the swap, advance 2 nodes forward, the odd case is covered. This while guard protects us. Now, I hope you've picked up some things about linked list problems as we've done these. I hope you've picked up the ideation. How do you come up with how you can approach things? It's all about writing a diagram, seeing how the pointers change from the original list to the new list, figuring out what's my guard going to be, what are the fundamental rewirings that need to happen, and how do my pointers advance. So there's 3 main sections: the guard, the main logic and the rewirings, and then pointer advancement. These are the key things, and you're going to see other weird pointer manipulations as we go along, but these are the fundamental things. If you can understand this, and you can also understand how memory works and how we shift pointers, then this is what linked list problems are all about. Diagrams and slowly, incrementally coming to a solution that covers edge cases. Now that we've seen just changing values, let's investigate the case that's a bit harder, actually shifting the pointers. This is the very beginning step in linked list problems. You won't know the answer when you start, but you will know the end list that you want to generate. And you're slowly going to build up your knowns as you go through the problem. So we see that B points to A. That tells us something. The new head of the list is B. The new head of the list is B. Maybe that's something we're going to have to take into account in our code. And B points to A. So that's another thing to note. We're going to need to point the second node in the pair. So let's conceptualize a pair like this. Again, we're just drafting our approaches. We don't exactly know how we're going to rewire things. But there's the first node, there's the second node. Now, the second node points to the first node. So we're going to have to say second.next equals first. We're unsure about sequence. We're just throwing ideas out there, and we don't know what's coming before this. Did we just destroy a reference? I'm not sure yet. What else do we have to do next? I'm not sure. But I know somewhere in the code, I'm going to have to point the B to the A. That's going to have to happen somewhere in the code. Maybe it might not happen, but I'm pretty sure it's going to have to happen because of what the output is. Now, what does A point to? A now points to D. What does D have in common to A? Well, if we visualize things as a pairing, this is a whole nother pairing going on over here. Now we started with our first pair, and then there's another pair. So there's the first node, the second node in the first pair, and then we have F prime and S prime, or we can just say the second segment, the next pair. Well, the first node in the first pair is going to loop over and point to the second node in the second pair, S prime, S prime. So A is going to point to D. A is going to point to D. So we can make that wiring, but what if that's null? In the odd case, what if it was ABC? Would A just point to null? This is tricky. We don't really know how this is going to influence our code yet, but this is something we're going to take note of. We'll just satisfy this even case, but this will influence our code when we go to write it. When we go to write our code, we'll make sure we cover this case. We need to think about that as well. And again, I'm just trying to walk you through exactly how you draft these answers because you won't know the answer at first. You need to go through the drawing, you need to go through the wirings. Let's just say first.next equals second segment start.next. That's kind of a long name, but we might need that somewhere. Now, before I do the first.next, remember how we said second segment.next might have a null? If that D over there in the original list is null, if it's just ABC, we're going to wire the A to a null. We might hit a null pointer. Or imagine, what if that second segment does not exist? What if the list is just A, B? We can't wire the A into the second segment.next because we're going to say null.next. Because if C is null, we're going to say C.next. We can't do a .next on the null. So then we need to take that into account. So there's probably going to be a null check here. Okay, so there's going to be a null check there, possibly. And then we're going to have to move our pointers. The first item is going to become the F prime. F is going to become F prime. first is going to become the next segment's first. And so on and so on. This is how we initially think about how we advance. And when we do it like this is going to work, and we're just going to have to cover a few edge cases with some if statements. But this is going to perform the rewiring. And then we have to advance other pointers. We're going to have to advance the second to second segment.next. But then we think about our while guard, the guard on the while loop. Well, we can enforce whether the second segment is null or not. That can also be something that we enforce, so we know if I say second segment.next, second segment is not null for sure. And there's so many ways that we can do these linked list problems. There's so many ways we can rewire these lists. This is why for a lot of linked list problems, you might do it one day, and then the next day you get a completely different solution for the same problem. You can approach these multiple ways often. Now, if we're in an interview, we might not want to jump into the code until we have a strict solution. But if we have a general idea of where to go, it might actually help us to begin implementing the code as we hash out these problems. And of course, we will test our code. After we write our code, we will do tests. We will test empty cases, normal cases, edge cases. Testing will always happen. But sometimes it helps you to, once you've crafted some base level cases, to actually start implementing the code slowly, iteratively, walking your interviewer through it, your thought process as you go, and then testing your code exhaustively. It sometimes helps to bounce off of a concrete example. So let's do the moving of the actual pointers, and let's craft that function right now. We created a function swap in pairs up here, and we're going to slowly craft our solution with a small example running right there. And we also can create an odd length list example as well. Now imagine we have a single item. If we just have a single item, there will be no pairs to swap. So maybe we can do a guard here. If we get an empty list, which is null, or a single item, we just return the head of the list. We just return the head we're given because we can't operate and do any swappings. So we can just protect ourselves off the bat. You don't have to do this. Your main logic can do that as well. It's whatever you prefer. So we can implement that now. We implemented that guard right there, and now we know that we need certain pointers. We established before we're going to have a first pointer and a second pointer for the first and second items in a pair, and we'll also need a pointer for the start of the next segment. And the start of the next segment would be C in that case. For ABC, it'd also be C. So that's 3 pointers that we can keep to cache values. So we have the first pointer for the first item in the segment, and the second item in the segment, we can establish those. So the first node is going to just be the head, and then the second pointer is going to be head.next. Both of these are going to resolve to values because of our guard up here, and that's going to establish that pair, that first pair we're going to work off of to perform rewirings. And let me write down the destination lists. And then, as I was saying, we also need another pointer for the second pair, head. So the next pair, after the current pair that we're holding references to, we need to keep reference to that head. We can just call it the start of the next segment and set it to null. Now that we've set up these pointers, we need to iterate through the list. We could just set up an infinite loop. We're not sure what our guards will be. We might determine them later as we craft our code. So let's just say while true and just continue looping until we can decide. Now what we can do is we can set up the start of the next segment. It's pointing to null right now, but we know that is the second node in the pair, dot next. It might be null, we don't know, but we still can perform that operation to set that. So let's set the start of the next segment. So the start of the next segment is the second guy in the pair, dot next. And this rule will apply to all pairs that we process as we move in the list. And that's just a general rule we'll apply. We'll see if it holds for the edge cases. And now we're going to point the second to the first because we saw we want to move B to A. We want to move B, we're going to point it to A. So point B to A. Do you see how we're slowly, incrementally figuring out what pointer needs to move to where? What are the patterns I'm seeing? We're going to start noticing some edge cases. I don't know what my while guard will be. What are the critical nodes that I need to hold to advance in my iteration and rewire with? What do my guards need to be? These are all things that you can be thinking about as you're solving these. And the examples are the greatest thing driving you to be able to craft this solution. Now we can point the first node in the pair we're holding to the segment start of next segment, which is the C dot next, because A points to D. Do you see how A points to D? So the start of the next segment where that arrow is, dot next is D, which is right there. We want to point A to that. But there's an issue here. What if start of the next segment is null? And also, what if start of the next segment dot next is null? What if D is null? What if C is null? These are things we probably want to check before we rewire this. So maybe this might be a case where we can exit this loop. So let's do a quick if statement. We might remove this later to simplify the code. It's kind of dirty to have an if statement within this and then break out of the while loop, which is infinite. It's kind of a tricky situation to be in, but it can work for now. So we're going to put an if guard and see where that puts us. If that is the case, if we have that start of the next segment equaling null, what do we need to do before we break out of this if statement? We're going to have to point this A somewhere because we can't just leave this A hanging. It's still pointing to B. So here, let me extract out a list. Here are two small cases you can look at. This case has C as the last node, and this case has a null as the last node, or a null as the next segment, because this pair is AB. That is the first pair. So I probably shouldn't put an X there. It just means null. I don't actually mean the character. And then this C can have a value, but then the start of the next segment can also be null. This is edge case identification. We're identifying what we need to cover here. It looks to me like we should probably point A to the start of the next segment in both cases, because A is going to either point to C in the case where this last segment is odd, or if the last segment is even, it's just going to point to null. A will point to null, and that's exactly what we want as well, because it would be BA swapped. We're going to point the first, which is this A, the first guy in the pair, to the start of the next segment. And then that covers that edge case. So that was the edge case of this start of next segment of the next pair not existing. Now we're just dealing with the normal case of having two full pairs, AB and then CD. Imagine two full pairs. Now that's what we're dealing with down here. So that means we actually can point first.next to start of next segment.next. That's the case we're dealing with now. All right, so that makes sense. Now that's going to wire the A all the way to the C. And I should probably update these drawings. Let's just update on the even case. So we wired B to A. And then we'll wire A to the D because we got reference to the head of the next pair and we have the next. And now we need to update our pointers. Where does the first need to go? It needs to go to C. Well, this guy, the start of the next segment, is C. So let's just point first to the start of the next segment. We've advanced the first pointer in the first pair. Now we need to advance the second guy in the pair. Where does the guy who is pointing to B go? He goes to the D. Who is that? That's start of next segment dot next. And that's not going to be null because we know this guard stopped us if that was the case. So both of these advancements will go fine. So second equals this guy dot next, start of next segment dot next. All right, and that should cover it. We've gone through all our edge cases, and now the next thing we would do if we were in a real situation of interviewing is we would test this. We would pull out an odd case, we'd pull out an even case, we would test both of them. And since we stepped through it, we can be pretty confident that all our edge cases were covered as we were stepping through. The final thing that would happen for this even list, let's actually finish it out, is we'd move the pointers to the C and D, so the F and S, come back to the top of the while loop, what's the start of the next segment, second.next, and then we would point second to its first node, which we'd point D to C, and then we notice that start of next segment is null. We'd come in here, we'd say first.next is the start of the next segment. So C is going to point to null, and then we just return the head. We'd get out of here because we don't have a complete pair to wire first to the second guy in the next complete pair. We don't have that, so we have to get out of this loop. So this is one approach to this problem. There's probably other ways you could do it. There's other ways you could rewire it. But this was the step through in the thought process behind this problem of swapping linked list nodes in pairs. And you're going to see this. We're going to use this pattern in all our other problems. We draw a picture, we draw little short statements of what we think will happen in the pointer manipulation, and then we're going to craft the code, and then we're going to check for edge cases, and we're going to continue like that, bounce between the drawings, and that's what it's all about. Now, this is going to run in linear time because we're going to be touching n nodes. In total, we're going to be touching all the nodes at maximum, and we're going to do constant work per node. All of these are pointer manipulations. This is all stuff happening in the registers and in memory. There's nothing that will scale with the input asymptotically. What that means is we have linear time and we have constant space. You're going to see this time complexity very often for linked list problems. This was swapping a linked list in pairs, both with shallow value swaps and also with deep pointer swaps.